Okay, so unmuted, ready to go. Let's see here. We open up.
I don't even have registration on a vehicle, so that's really yeah, and I'm angry. And now they're gonna see that I read it. Got I
Okay, so we still got a bit of material to go. Several assignments, well, two more assignments, I'm gonna say. So we have, we had the technology one, we had the transmission line as well. So we'll definitely have one due. What is it today? The 13th. Yeah, we need to have one due in 2 weeks and then one due at the end of the term. I just want to make sure that all the material covered in the final will be tested in some shape or form in the assignments. And I know I said I was going to have those ready for you. I promise it will be done before Friday. Okay, so all assignments will be up to date, marking, and so on. If you happen or have an assignment that's incomplete, just you literally have until the end of the term, but I suggest you do it as soon as possible, right? Yeah.
the assignment further like review and you're going to send back. Are you gonna send back like solutions? PDF to the questions?
Oh, well, you want it now? I usually provide them at the end of the term. I got one whole PDF PowerPoint that has all the solutions for all 5 assignments. But these ones are slightly different with some numbers, so we have to do some crunching, or sometimes I just give you the solution for something similar and you guys can look it up, right? What to do in the final, make sure you attend the final review. It likely be online because I don't think we can find a time for you, all of you guys. And I know this is a small class, but even then, for all of you guys to agree on. So we basically just do it on Teams and record it, right? Probably the best. Okay. Yeah. So we need to cover a little more about PLLs, some of these blocks, and we need to talk a little bit about equalization as well. Okay. Anything else? So we have 3, 6, 9. Wow. So 9 out of 23. So we're almost at 40% today. Yeah.
You mentioned you were going to use the solutions to some of the assignments before the end of the term. I'm just thinking we only have like, I think 4 days after the term.
I'll release them as soon as I'll separate them and release them in the next couple of weeks. Okay. So you guys can have it. Yeah. When is the final? Whoa, 13, yeah. Okay, no, for sure. So we need to. We probably have the last 2 lectures of in class as reviews. Then, I mean, they may force you guys to. So let me work on that. I think the last week, Fridays and Monday, right? Okay, so if we do Thursday and Friday, they'll be back to back. There you go. That's our. Oh, actually, we don't have classes on Mondays, so we wouldn't be scheduled. Okay, we'll do the last week of classes. We'll do Tuesday and Thursday as a final review, regardless. Okay. Okay, so yeah, that's a good point. What time is it? The exam?
Oh, it's 2 p.m.
2 p.m. Okay. All right, that's early. Yes. I mean, I can comment on Discord for everyone. Post it up there, and then we'll definitely go for that. Sure. Yeah. Okay. So we need to cover a little bit about PLLs, clock distribution. We talked about phase detectors, and we have two types of phase detectors. We have a linear phase detector that just basically just measure phase as a function of, voltage as a function of phase, as you did with the Hog type of linear divider, type of phase detector. And you can see linearly how the voltage of the output loop integrator actually works as a function, right? Then we have a similar way of doing it using a non-linear or oversample. So we oversample the system. So we do more samples than the actual that data rate is. And then we actually examine the behavior of it. What happens before and after. So we have all these EN, decision making EN, and then EN plus 1. And based on that, we can tell whether the sample is late or the sample is early. Okay. And then this is an implementation of that using flip-flop. Oversample it, take 3 readings, S1, S2, and S3, right? And based on that, you have to compare S1 and S3 and be able to tell exactly what that is. But there's another condition that we need to worry about is what happens with the frequency. So there are situations where we could be in phase, but could be a different frequency. How do we know that, right? So typically, when we look at modern systems, we don't do just phase detection, we do phase frequency detection. And all it does is a condition where the up and downs are the same. So that triggers basically a reset on it, and that is set to say that we are actually now in sync, right? When the reference and the actual up and downs are together, then we basically generate that reset point. And that's effectively what generates the frequency. So we can do phase frequency detection. This one here has to do with the conversion. Okay, so we got phase. What do we do with phase? Well, the phase has to drive an oscillator. So we did the system overview of that on the previous lecture, and we got all these up and down pulses. And what we do is we steer current. So we have this current steering mechanism, which we call the charge pump. And literally just pumps charge up in and out of a storage element, which is a capacitor. And if the system needs a little bit less, we take charge away, so the voltage goes down. And if the system needs a little more, then we add more charge, and effectively your voltage goes down, right? Because effectively you have Q equals CV, right? So there's a direct relationship of charge and voltage, right? So this one, effectively, again, the purpose of it is to convert the output of the PFD into signals that actually are used to charge a storage element. Which in our case is the capacitor in the actual loop filter. Why do we need a loop filter? Well, we can simply have a capacitor, and we talked about that. But the problem with the capacitor is that it's very difficult to control the actual natural frequency of oscillation. So we're basically moving up and down, and the damping ratio. So we got damping ratios, and we also have this natural frequency of oscillation as you're switching back and forth, right? And those are dynamics of the PLL. So the loop filter, one of the purposes is to basically control the dynamics of the PLL. And that's an extra degree of freedom that we need for stability, for the bandwidth. So if you look at, have you guys ever seen the output of a PLL? Like in frequency spectrum? So let me just introduce one here. So if I go and page after square paper here, right? So if you look at an oscillator, and then we control it with a voltage, right? So what we typically have is you will have a spectrum that will sort of look like, so here we have power as a function of frequency, and then you have your center frequency, and then from that center frequency, you will have something that does this, right? That's a real signal source, right? And then the power away from the center frequency is measured in terms of phase noise, right? It's how much power away. And so phase noise is typically presented in the form of a dBc over hertz, because we actually integrate it, right? So at an offset, okay? So if I say to you that we have a phase noise of minus 118 dBc per hertz at 1 megahertz, it basically is the integrated power normalized to hertz at a 1 megahertz offset away from the center frequency. So this becomes 1 megahertz. Okay. So dBc, because we're actually not measuring with respect to absolute, but with respect to the carrier. So we always actually make, so the carrier, whatever the number is, 0, minus 5, minus 10 dBm. But we don't care, because it's basically with respect to the carrier, which is a more representative number as opposed to be looking at this, right? But if you ever look at an oscillator, you basically will have trouble capturing what I just showed you here, because the oscillator is going to be jumping up and down, right? The frequency and the phase is going to be all over the place. It's going to be very nervous. So you can kind of like stop the spectrum analyzer and kind of see what you have, but you can never capture it because it's not locked, right? So when we actually put it into a phase lock loop, so we have an oscillator, goes into a divider, then it goes into a phase detector with a reference, and that goes into PFD, charge pump, and loop filter. Sorry, I ran out of room here. And then it goes your output. Sorry, your output will be taken out of this side here. Okay, so the actual spectrum now actually looks like effectively, so you have your center frequency, and then you got something that looks like this. Okay, and what you've done is that because of the feedback mechanism, you've actually suppressed the noise within the bandwidth of defined by this loop filter. So the loop filter basically defines the bandwidth. So as a result of that, the filter dynamics are one that would actually help us with the natural frequency and the damping factor, which is a matter of stability. It would also help us with noise, and would also help us with locking range and bandwidth, right? So the wider the bandwidth, the easier it is to lock things, right? The less nervous things are. But as you can imagine, when we actually open up the bandwidth, we also introduce noise. So lots of considerations, right? So from that point of view, again, let's go back to the loop filter. That's what we're talking about. Is the dynamics of the PLL with consideration of stability, noise, and range. All right. So, and that's exactly what we do here. So we're not going to define transfer functions. I think those are just representatives. We do have full courses at this certain level that will basically deal specifically with PLL. So I don't want to bring it up, because if I bring it up, I have to then quiz you on it. But there's some examples here of what it does. So you got a C1R and a C2, right? And it's effectively low pass filter extracts the average of the phase and the detector error pulses as well, right? So here's an example. So if you look at the transfer function of these, you have effectively VC over IE, right? And that is actually equal to R plus S plus 1 over RC1. So you effectively have a pole, and then you actually have a 0 that actually compensates that at effectively the location here, which flattens out the response as shown here, right? Okay, and then someone designing a PLL will now have to consider all possible cases, and it's quite complicated. You pull one way and you give up the other. So very challenging to do this. There are systems out there. If you're ever trying to design a PLL, I know Analog Devices has a PLL designer that would actually, in real time, allows you to plot phase noise. So if you actually go, I think it's called the ADE, Analog Devices PLL Designer. And you basically got a whole system with a PLL, right? That has your charge pump, your PFD, your VCO, your divider, and also the crystal. And what it will do is it would actually give you effectively the VCO. It would actually go the loop filter. It will do all sorts of components, but at the end of the day, it would also give you the total noise integrated, right? And that total noise integrated is actually what you're trying to target for a system specs. So then you can basically change the values of the loop filter, design the correct for the current and the charge pump, the phase noise on the oscillator. You know, if the phase noise on the oscillator doesn't match the response of the filter here, what you would have is you basically have something that does this. And we actually call those ears. And that behavior right there, it just tells me that the actual loop bandwidth is not corrected for the optimum behavior of the VCO. So we haven't done that. And the spurious and all this other stuff, which we're not really going to get into it in this course. But anyway, the dynamics of the transfer function as well, right? And then by introducing the second capacitor, right, we now have the first pole, but now we actually have the first zero, but we also have now a secondary pole, which is introduced as well. And why is that important? Well, that actually, again, helps with the dynamics of the PLL, specifically the phase stability, making sure that the actual loop is stable. And it also acts as the integrating element. So a lot of the charge that we're putting through is actually charged on storage elements C1 and C2, but mostly on C2. Right? And the other thing about C2 as well is that it also helps us, because one of the problems with without having C2 is that this PLL would have done something like this, right? So by actually introducing C2 is actually acting as a filtering element. So it smooths down the wave, filters it, right? So C2 is mostly for filtering, and C1 and R basically control the loop bandwidth of the system as well. And here you go. Why? Why have C2? The secondary capacitor smooths the control voltage ripple. So you got this ripple, and when you add the capacitor, you can actually minimize it. You can't make it too big or loop will go unstable. And so C2 has size constraints, and those are defined depending on whether you're targeting stability or whether you're targeting low jitter. Right? Those are the two things I mentioned. There you go. The last one, I think we talked a little bit about that, is the transducer of the oscillator, voltage to frequency converter. And that's a pretty powerful thing. Oscillators are used in various applications. I had a company in Kanata, actually, in Maribel Road here, that was actually doing sensing of, they were doing control of nano inverters. So the grid has 500 volts, and that's basically going to a solar panel. And then what do you do with that, right? How do you sense what's going on? Because as I'm told, and I'm not an expert in this area, is if you have a farm of solar panels, your efficiency can drop drastically if you have a few rotten apples within the system. So you got to constantly monitor efficiency. A few panels can kill the efficiency of the whole system. So you got to monitor what they're doing and shut off the ones that are not helping. If you got an entire farm, but a little bit of that is in the shady area, and they're actually depleting your efficiency as opposed to helping it, then you go back and cut it, right? So you need sensing. So how do you know how much current is happening at the same time? So one of the students in here said, we set him out to do something which was a current to frequency converter, because it's difficult to actually, and we're doing this with a chip, right? So the challenge there is you got 500 volts on the grid, and then you got 5 volts on a chip. So if there's any kind of capacitive effect there, the 500 volts are going to overpower the IC, and before you know it, you actually hit one of the rails. You're done. So what they use there is something called a galvanic isolation type of circuits. So they use inducted paths to be able to remove stray capacitance between the grid and the IC, keeping ICs away from all the extra noise that comes from the grid is extremely difficult. So one of the things that we did is we actually put an oscillator that was actually measuring the voltage across a 1 ohm resistor. That's really what we did. And then as a function of that, it generated a voltage, and that voltage is measuring capacitance. So if the current went up, the frequency changed, and then we have a way to tell, right? So oscillators are used for that. We have actually used oscillators to, to measure coupling mechanisms on chip areas as well. As part of my thesis, some 30 years ago, one of the problems is what happens if you have, and you guys have seen an RFIC, right? It's made out of a bunch of inductors spread all around the chip, right? But this environment is highly uncontrolled. No one knows how to model this. It's too complex. It was too complex back then for computing power. It's still too complex. We cannot do a full chip. And I hope you guys know that. A lot of the guys who are actually doing circuits here, when we put a massive circuit, we're still 2025, we're still just sending pieces of it, evaluations. We never can do a whole evaluation of the chipset. It's too complex for us. Hopefully, quantum computing and artificial intelligence will help us with that. Anyway, the point is, how do we measure the coupling from inductor 1 down to inductor 5? Okay, and one of the ways to do it is to actually have oscillators that are identical oscillators that are placed apart, and now they're talking to each other. And then we see how one moves with respect to the other. And if we do the transfer function, because they are the same oscillator on the same chip, a lot of things cancel out. And effectively, that dV difference is directly proportional to coupling. So we can use it for that. And the purpose of a PLL is effectively a transducer that does voltage as a function of, frequency as a function of voltage. And we have the time domain characteristics of it, is to find that the actual phase out of the oscillator is equal to some constant value, KVCO, which is represented in this linear region here, where we actually get phase or frequency, one is related to the other, as a function of voltage, right? So from a Laplace domain point of view, we have a 1 over S characteristics, right? And you have a 1 over S, which is here. So you got the 1 over S. And then you introduce another one as well, and then you basically turn into a second order system as well, right? Which is shown here. That's why it's a second order PLL, because the first order comes directly from the oscillator. Okay, how do you build oscillators? Have you guys ever built an oscillator? If you're in 4609, you did. But one of the ways to do it, which is actually quite simple, is to take an inverter, right? So if you have a 1, you have a 0, and then you have a 1, and then you have a 0, and that 0 is actually fed back. And if you have a delay per cell, we're going to call it a cell tau or delay, and then you have the same across from that, you can actually know that the frequency is actually 1 over the period, right? But the period is actually a combination of all the delays that you have. So if you know, for example, if you build a 20-stage door, well, actually you can have a 20, but if you could, it has to be an odd number. But if you do a 21 stage, right? 21 stage ring oscillator, and you measure that the frequency is equal to 21 megahertz, then you can actually go back and say, well, I have 21 stages and I have that frequency. So then I can exactly what the delay of that cell is. So oscillators, we use them as performance indicators in an integrated circuit to actually tell us what is the internal delay of the cell. Right? Why do we do it this way? And why do we just measure the delay of a cell? Question for class. Why do I have to build an oscillator to measure the delay? Why don't you just basically measure the delay of each one of these? Exactly, you said it right there. Trying to measure a delay by loading it with something else would actually mask the behavior of the circuit itself, and it will be very difficult to decouple one from the other. While if I do it this way, you know that one cell is driving the other. It's integrated. It's organically made into the system, so that frequency is pure. It's what it is, and we just basically just use standard arithmetic to actually be able to extract what that delay is. Very simple. Now, so ring oscillators, very easy to integrate. It's the easiest thing to do, right? And you'll be surprised. You put 3 of those guys and you connect them and they start to sing like a canary, right? Easy. Although I must say that simulating oscillators is not as easy as measuring oscillators. Any guesses from you guys? What would be actually more difficult to simulate an oscillator than to actually measure it? Usually the other way around, right? Measuring is a real pain. Simulating, you just put it into a simulator and make it work. Because imagine the simulator is a very quiet, lonely place. It's like almost being in outer space, vacuum, nothing there, right? And what the oscillator does, again, it has basically a loop gain, and it just integrates noise. And it basically, if Barkhausen criteria is met, it just starts to oscillate, right? But in a simulator, you actually have to mimic that behavior. If you don't mimic it properly, the oscillator just sits there and does nothing. So you got to kick it. So you often will see, and how do you kick an oscillator? Well, ways to do it is you could, instead driving this, so imagine if these are all driven by power supplies. Okay. And then that power supply typically is just a VDD, right? That won't work. So what I have to do is, okay, and then that VDD, let's say, is 3 volts, for example. So what I have to do is I have to actually replace that VDD by step. And the step is going to go from 0 to 3 volts and stay there. But the actual transition from going from 0 to 3 creates imbalances in the circuit, and that basically gets it and kicks it into oscillation. That's one of them. So we can do voltage imbalances, or often, if you have a differential path, so you got a differential path, and then you can basically introduce a current in between that effectively just kicks it and then goes down to 0. So it just does an initial transient condition that it basically just unbalances both, gets it into oscillation, and then it goes back to its regular value, right? So you can do it in multiple ways. So ring oscillator, easy to integrate, wide tuning range, and we'll explain that phase noise condition later, but it has higher noise than when we use the second one, which I'll explain in a second. Now, an oscillator is useful, but it will be more useful if you can control. How do we control it? Well, we actually can introduce biasing into it. And biasing, if I bias an inverter, what am I doing? If I take an inverter, a CMOS inverter, right? So you got a PMOS, you got an NMOS, but I can then control the biasing on both ends. And I can actually change the current, IP, IN, if they're not exactly the same. And I'm looking at in and I'm looking at out. What happens when I change that current? What sort of behavior learned in this course are we exciting into this inverter? We actually call this a starved inverter. We will start to play with its current density. And as a function of current density, it is going to have a different speed. And as a function of speed, the frequency will be now changed. So we're changing the current. We're changing the actual current density of the device. You could say the parasitics internally as well, but really it's all about also about making sure that we're switching on and off the current behavior, because remember, speed and current densities are all related, and current densities are all about periphery and current driven into it, which can or may not relate directly to capacitance value, but that's what we do. Change the voltage, changes the current, and that effectively now drives the frequency to be tunable, which is what we want. That's hence the term VCO, voltage control oscillator. The second way of doing it, and I think I explained to you guys before, is you have oscillating elements. You have an L. We're just going to look at it. So you have an L and you have an L on the other side. And if you put an L next to a capacitor, then energy must be conserved, right? So you have magnetic energy and electric energy actually going to start to exchange. And they're going to do it so at a rate equal to the oscillating frequency of those two elements, which is 1/2 pi squared of LC. but those oscillations are going to dampen because of the nature of the fact that everything in real life have losses, right? So here, the capacitance is not explicitly shown, but we know that if we actually take a diode and we connect it opposite direction, so typically a diode, you have the positive and you have the negative, right? But if we connect it the other way, guess what I have? I've actually now generated a variable capacitor because the depletion is actually now controlled. And the capacitance is now controlled by the voltage difference between the plus and the minus points. Okay, so this voltage here on the ends is fixed and controlled for both. So if I was to actually monitor and control the voltage in the middle, I'm effectively controlling the difference across those diodes, and they're symmetric. And hence, I'm actually have a variable capacitor, a voltage control capacitor. So that's your capacitor. So you have your L, and then you have your C variable and C variable, but they all have losses. You have your L and you have your C, and then as a result of that, they also got something called a positive R. So if you introduce a cross-coupled device here, and you actually introduce a negative R, the positive R and the negative R cancel. The LC now is free to oscillate. There's no losses, and this circuit can now explode to infinity, which is not a good thing. So I explained in class before that also the fact of using ideal transistors, the transistors saturate. They cannot amplify and conduct forever. So as a result of that, it's going to be a feedback mechanism that is going to control the amplitude, right? So the losses will be controlled. This oscillator is going to be freely available to oscillate at the frequency that it wants. And then there's a mechanism of controlling the amplitude by the actual saturation conditions of the transistors, M1 and M2. So a lot of stuff going on in such a simple circuit. Berkhausen criteria. Okay, so we know that for sustained oscillation, we must meet two conditions. There's 3509 material. Or we have a feedback system where transfer function equal to h of JW1 minus h of JW. Sustained oscillation will occur by actually making equating the denominator, which sets that h of j omega must be equal to 1. What does that mean? Right? That the loop gain must be at least 1. Right? And I explained to you what that's not necessarily true, but that's what we started. So two conditions. The phase around it has to be 360, so it actually is adding constructively, not destructively. It's not canceling out. So we have a plus and a plus sign here, which is actually done on purpose, right? So we're adding it. Secondly, is that the loop gain has to be greater than 1. But this is not correct. And I think you guys learned about that in 3509. What does it have to be and why? Yeah, so the h j omega has to be greater or equal to, let's say, 2. I use a number there, right? Because you actually have internal losses. So the total phase shift is an multiple of 360, and the gain has to be 1 or greater than 1 at the oscillator frequency. Okay, the loop divider. Okay, so loop divider is for the most part, is a digital cell. The problem with having a digital cell is that typically you make digital cells out of CMOS inverters, right? And a process, so you have your input and then you have your output. And any process will have different flavors of this. So let's just go back and just define some conditions. For digital design, okay, for digital design, the actual maximum frequency of operation has to be less or equal than a factor of the FT of the technology. Okay, you guys know what that number is for digital design? So if the FT is 100 gigahertz, what do you think the maximum frequency of operation of a digital can be made out of it? 50, no, too high. It's about 1/20th of it. Okay. So if you have 100 gigs, it will be half a gig. And this number can vary depending on who you talk to, but it's typically anywhere between 1/10 to 1/20th, somewhere along there. All right, so that's a problem because we got, effectively the VCO is outputting frequency. We're going to go this way. So the PLL is actually this way, right? So you got your loop filter, you got your charge pump, you got your PFD, and then somewhere along there. So this frequency, which is high, has to hit this cell, which is a digital cell. And that cell has to work at 1/20th of the FT. What if I want to go higher? I'm out of luck, right? So it is a problem by using this type of cells. So we either need to use a starved cell in which we actually control the current density and hence high frequency behavior, or we actually go, so we can either use a starved inductor, inverter, or we use CML. Right. So the first few stages of this divider are typically fixed and they are CML. You can do programmable, but it's not often practical. So we got an oscillator. That oscillator is going this way. It takes a divider. The first one will likely be a divided by 2, as I said on Tuesday. Then we have a divided by 2. Then we have as many dividers by 2 until we meet this condition, which is to be 1/10 to 1/20th of the FT of the device, right? And that's it. So the actual frequency is one end of the output frequency, and then we can basically do something simple internally, right? There's various ways of doing it. Simplest way to do it is actually just put 2 flip-flops side by side, right? And then you have the in and the in plus. And if you look, and then you basically just loop one of the Q bars back into it. So if you look at it, if you look at the transfer function, you have the T, the period of the input and the period of the output, and you've actually effectively doubled the period, so you have half the frequency. So that's a divide by 2 using a flip-flop in negative feedback configuration. And the important thing of it is actually looking at the transfer function, right? So in the operation, so we have the VCO frequency as a function of time, and then we can kind of see the dynamic of that loop as well, which has to be taken into account. How do we actually do that with a CML? We can actually use a CML as well. And if you look at that back, right? So we had a CML with resistors. So you got, so a couple of things going on here. You basically have all these latches, which are actually helping make the D-flops itself. The clock is actually sent positive and negative, and then you basically have the feedback loops as well, right? So you take the output directly out of here. Okay, and advantages, CML levels, signal only propagates 2 gates, so it's fast. Disadvantages is that it's larger because all these devices typically have large periphery, which is needed for controlling the current density, and it also has static current consumption, right? So you have all this current consumption here, which is a problem when you do things. So what I've tried to say here is when you have dividers, they actually are power hungry. Okay, so for the assignment, we actually will look at maybe, I'll show you how, for example, we do programmable dividers. How do we do a divider by 3, by 4, by 5, right? So we'll look at those probably on Tuesday, and those will be captured in the assignment. So from here, what have I asked in the past? oscillators divided by twos, and some obvious CML type of questions. We'll look at some of the questions that I've asked, but kind of understanding the behavior and what the pros and cons will be, some simple analysis. How would you fix a problem, or how would you make it better? Like sort of using a combination of all of these, right? Okay, so disadvantages are larger size and dissipated static power. We also have, you need a differential input, which can be a problem, right? Differential inputs can be a huge problem, especially when you have clocks, right? Because the assumption that we make here is that the clocks are at 0 and 180 degrees, right? That's what plus and minus means. Do you guys have any idea how difficult that is to achieve over a clock distribution system? And what happens if it's not 180? What if it's 173 degrees or 163 degrees, right? What kind of, because the conditions on which this is assumed is that when you have 0 and 180, you basically can generate things like, for example, what happens in this node here? What happens if you have exactly 0 and 180? That storm resembles a person being in the middle of a hurricane. And what do we call that condition in electrical engineering? An AC ground. Because one's swinging up, the other one's swinging down, which can be seen here and can be seen there. So if you're on the outer stages of the hurricane, you're gone. But in the middle, you got equal forces pulling you the both ways. So from your point of view, you're not moving. One's moving too high, one's moving too low, but you are actually in the center and you're not going anywhere, right? So that's, in that condition is super important for the actual equivalent circuit that comes out of the circuit. If that's violated and you don't have there, then what you got is some final resistance of some value, right? And that throws things out of the door. So the analysis becomes more complicated. Binary dividers, asynchronous versus synchronous. So you can have asynchronous dividers, which are basically effectively driven on, so the actual VCO frequency is the clock. The asynchronous, right? There's no internal clock, which is the case for the synchronous dividers. And they're super fast, right? And then basically reduces a lot of the stuff that comes from the clock. The clock can be a very tricky thing to do, especially when we do PLLs. I don't know if I told you these guys, but one of my first jobs as an RFIC designer, and typically this is what's going to happen to you guys, is when you first join a group, right? And say, oh, there's a new guy over here. Well, let's make him look like he's part of the team. Give him a small little circuit here, which they did. And after that, into the lab. And in the lab, I spent 2 years trying to reverse engineer what this complex chip for everyone else was. So the senior designers move on. You finish a chip, you're giving a new task, and you go away, right? My job was to stick with this thing for 2 years. So I learned a lot about it. And then you basically are chasing them down and says, you know what, why did we do this way, and simulations and all this stuff. I'm not seeing this in the lab. You got to work, but it is all part of it. There's the science behind it. It's the fact that you really have to immerse yourself with the nature of how the group works, because a lot of these schemes are actually carried over from chip to chip. And then you also get to really understand testing, which is, you know, another domain into itself, right? So anyway, as part of all this stuff, you get to go to, you know, I was working for a company called Skyworks at that time, and we had design centers in California. So I will travel every 3 weeks and meet with test engineers. One time I was so proud of myself for actually doing a MATLAB routine that would actually do bit error rate testing back and forth within the chip, and it will take 19.2 seconds. I was like, wow, that's awesome. Super fast. You can do all sorts of stuff, right? I take it down there and I go into a different world when I went to the testing group. First of all the equipment had no displays, just refrigerator like black boxes, and no MATLAB, no Windows. So all driven from, what do you call that? Assembly language or C, worst case scenario, and stripped down as simple as possible. So their goal and their philosophy is to make it as quick as possible to test the chip, because they're doing millions, billions of chips, right? So 19.2 seconds, with an amount of chips that we have to do, we're dead. We have to be less than 2 seconds. So they took all the stuff that I did, strip it down. What do you need? So the basic question is, what do you need to test a circuit? And then, everyone says, well, especially grad students, oh, we need to test phase noise. We need to test frequency stability. We can't test that in real time if you're doing 7 million chips a day or more. So the question is, what is the 1 or 2 parameters that would tell me whether this thing is operating properly or not? And typically that is current. It's never voltage. Voltage doesn't matter. Voltage is just a condition that we must present at the inputs to basically bias the device properly. It's really current that drives it. If the current flow into the device is correct, then that actually defines the perfect AC model that you use in simulation, and your results are often bang on, right? Which is what you want. So a lot of these, so anyway, what I was trying to get is that I noticed in the lab that some of my channels on the PLL were gone. And I said, well, why is that? So we had a PLL, something on the extent, if I can remember, we had a chip, right, that had an input. I remember very closely here. So this is basically the external clock. And it was a 9.2 megahertz TCXO, temperature control crystal oscillator, okay? And then we had an engine of this extent, which is effectively was our digital engine. And then somewhere in here, we actually had a PLL, which had an inductor on an oscillator. And then you had this clock going something like that, right? So what I noticed is that the 66, 67th, and 68, sorry, no, I'm giving you the answer already. I noticed that some of the channels were actually knocked off, like they were gone. I couldn't get anything out of those channels, and I was testing every single one of them, right? But it works out that if you do them, and then I started to look at it and say, well, what else can I do? And typically, a lot of these components will have their own supplies. So we have the supply 1, and the digital will have the supply digital. So if I actually bring down the supply of the digital, the channels will come back up. So what it turns out to be in the end, which was clear as a whistle once we figure out, is that this clock in its way into it was actually coupling some of the energy onto it into a very sensitive oscillator. Remember, I said the oscillator is the most powerful amplifier ever built, and efficient, right? Because it takes noise and it amplifies it. But if that noise is within the oscillator frequency, it can also destroy it, right? So what was doing is that this oscillator, if you actually go by, sorry, this crystal oscillator, if you do the 66, the 67th, and the 68 harmonic, so these TCXO, if I was to look at the response, you had 19.2, but then you had harmonics. And those harmonics go all the way. So somewhere in here, at a very low level, the 66, 67th, and 68 harmonic of that were actually fighting its way into that inductor and causing trouble. So how do we fix it? How do you fix this problem? You can't get rid of the clock. You need it. Any guesses? Separation does so much, but what else can we do? And actually, it's something that designers do in high-speed circuits because the integrity of the signal, right? Any guesses? And you actually have done that in 2507. In fact, every bench in 2507, 3509, specifically from the supply or from the clock, actually uses the very same technique that we actually use in an integrated circuit, which is called so the oscillator is bringing us noise. We want to suppress noise. How? Yeah, filter it. Huh? No, we can't. We can't put a bypass capacitor. Okay. What we can do is something that you guys have seen, which I'm going to do here in red and black. What do we call that? A twisted pair, right? Where the black is the ground and the red is the signal, which is the TCXO. So what we did, which is actually incredibly effective, is to take these into an integrated circuit, and we do this. We actually go with the clock. Okay, and then we take another layer. And we do that. Incredible. I just basically, that knocks off the suppression of noise is actually reduced by 20 dB or better. Amazing. And that solves the problem. You can do the other things, like you can, for example, bring an additional layer of ground, and you can do something like this. So shielding this path obviously adds more area, but it's so needed if you want this to work.
Yeah. So this is the clock.
Yeah.
But like
Why you use the clock?
pardon me, like how does it reduce noise?
The actual common mode is now percented, right? So it's the same idea, right? So this is why we actually reduce the common mode ability, the ability of generating common mode into the circuit. Yes.
In this case, just you testing and ship those are.
Well, so again, so what happens when you're a junior engineer in an IC team is, and by the way, a junior engineer with a PhD, and so that's why at that time what it needed. Now the standards are different. But I was the younger of all the guys. These guys were gurus from Nortel, and they all have circuits named after them and all this stuff, right? So it was a very interesting team that I joined. But anyway, so they basically built a massive chip. We're building in the extent of 10 to 12 chips a year, and this happens to be one of them, right? And this one was actually built by the whole team. Taped out, came back, and then we needed someone to test it. And the best thing to do is get the junior engineer, because he's going to learn how this thing works. He's going to learn stuff in the lab, lots of useful things, and then effectively, we don't really need him because he's kind of the junior guy. He's going to join us later, right? So sort of. So yes, and we were working across multiple platforms. So when you took 4609, if you did last term with me, I gave you a glimpse of two tape outs, a mini tape out and a full tape out at the end. But these guys here are running on about a tape out every 3 months, and different designs. Like one is from XFAB in Germany, followed by Huahong in China, SMC in China, or Global Foundries in Taiwan, followed by many others. Yes. But yeah, there's a single-ended clock. Yeah, yeah. That's one of them, right?
So, I guess you won't really be able to solve the problem of having a differential clock.
Yeah. So okay. So here is another piece of information for integrated circuits, right? So a product, I think I said this already in 4609, but I'll repeat it now. So a product cycle takes 3 times. So the first one, we actually just call it we call it a technology evaluation. And then we have a almost 90% ready prototype. And we have production. Right? Those are 3 tape outs. Tape out 1, 2, and 3. I joined a company in Canada, and I hope that whoever did this is actually listening to this lecture, what I'm saying. And I said 7 years ago that we needed 3 tape outs. And the CEO of the company challenged me. Garbage. That's your problem. Your old mentality, finding a way to actually stop the innovation of the start. 7 years later, because we didn't do things right, we're chasing that 3rd tape out. Because if things would have been done properly, people do this for a living, right? Is that on the first one, you evaluate what you have. Point in case. We're trying to change the world by combining SATCOM and 6G cellular bands. That's a big hot thing, and I'm doing that right now. I'm working with China. I just got an email saying that my accounts are ready. Okay, we're changing the world in that sense. But the problem with innovative solutions is that at the academic level in the university, which I kind of tend to be more towards the industrial side, we can solve a problem, and leave it there, but no one can use it. I don't know if you guys ever heard about phased array systems. They change the phase between antennas and all this stuff, right? They've been around for 30 years. No one's using them. Why? Because the problem is not solving the problem. It's solving the problem by using a cost-effective solution that anyone can use, right? So when we go into this, it becomes an engineering production by definition has to be an engineering effort. So we can evaluate the technology. We looked at the most critical fundamental blocks and we just say, these 3 blocks are the ones that could cause us trouble. The rest will be okay. Let's emphasize those. And we do a technology evaluation and then we come back with an answer and say, stop, we can do something. Then we build it, right? And we build it maybe too big. We do too much of it, but we end up in the second tape out doing something that is 80 to 90% all of it. But stuff still comes back. This chip was in the second one. So then when we got the last one back, right? But the question always is, and if you ever become an RFIC designer, you know, you heard of unicorns and all this other stuff, right? They always ask you when you join a team is like, how many first silicon designs have you participated in? And then they will tell you, I've been in the industry for 35 years. I've had 3. That means that you guys got it right on the first time, but no one actually gets it right because what interesting thing here though is that we never tape out a third on this one. We never did the third one because this was good enough. Those three, sorry. So how we end up solving this problem is a combination of controlling the VCC of the digital, which we could quiet down to recover those channels, and doing all sorts of internal tweaking. So we produce not a full-blown athlete that was going to do the 100-meter run, but something that kind of walked a little sideways, and then we gave it back, right? It was a market in China at that time, and then they needed it. We send the chip. They actually were able to make a call. We're done, right? But in reality, what you do need is all these 3 tape outs, right? Here's an example of a dual model prescaler. We'll go through that. What time is it? We'll go through that on Monday more carefully because it's part of the assignment. So I want to make sure that we do this properly. But this comes out of Rasavi as well. We can do things like divided by 2, 3. So depending on the value of MC, MC is equal to 0, we will divide it by 3. If MC is equal to 1, we will divide it by 2. And then the key here, though, is that if this can be done in CML, it can actually be put right in front of the oscillator. So we need to have 2 flip-flops, latches, and 2 gates, an XOR and also a AND gate, right? Or you can have a divided by 15, 16 here as well. Okay. So, and you can also have, if it's synchronous, you can do a divided by 3, 4. If it's asynchronous, you can do a divided by 4. It's a whole bunch of topologies and architectures to do all of that stuff as well. And we'll not necessarily use it here, but we just basically just overall cover and learn. So we'll try to do an example of these on Tuesday. The 2 divided by 2. And it's actually part of the assignment, so limit of what I want to give you, but at least I'll show you how to get it started. Okay, this one here is a blind oversampling CDR. So now we're getting into the last few slides that shows architectures of all these PLLs. What do we do with them? But in this case, we have single stream of data, a bunch of parallel samplers, and then we have phase detection logic. Then we basically recover the data. So we do some kind of a bit boundary detection of that. And that is done through the generation of multiple phase generators. So we know the phases are coming, and then we basically do a detection. And when we match it, when we actually match the data to one of those predefined points, then we know what we have, and then we just start recovering the data, right? So the incoming data is not synchronous with the reference. So there's no recover clock. And a decision is made on a majority vote result as well, right? So you can either have CDR or you can actually have a decision making on majority. That's what they do here. So this is a blind oversampling CDR that performs phase detection and data recovery without actually doing clock recovery, if that makes sense. Here's another example, very similar to some of the ones that we've done in our case here, but you have an incoming data, okay, forget about the layers beyond the scope of the course, but you have then a phase comparator similar to what we've done here, A, B, and C. And that basically generates up and down pulses, increment, decrement, and then we have a clock phase pointer that rotates up and down, right? And that generates clocks that are now used to select what's called an interpolator. So you have this interpolator phase system here that actually generated from an internal clock, right? You have a phase interpolator that generates all the different phases, and that's basically used to generate the clock phase pointer that sort of controls which one to select doing a comparison. So 3 samples of data are taken by the clock, right? The majority of all results advanced delay adjust the phase on a single step. So you're able to tell if it's too slow, move it fast a little bit. If it's too fast, move it down a little bit as well. Okay, phase picking, CDR architecture. So there's another one here, right? So you have reference phase. So you have these NRZ data, input buffer, into it, and then you have some kind of a reference clock internally, which is phase effect, loop filter, VCO divided by N, so that's the PLL. And that phase VCO is now generating multiple phases. And then this goes into a phase selector, which is actually controlled out of the output of the phase detect into a loop filter that actually smooths down the signal, and then a phase selector interpolator that actually helps us. And that actually goes back into the real-time data, right? So you got the data going all the way to the real-time latch here, and then the actual clock of it is generated out of the feedback mechanism generated by that phase detector. Okay, and for the ones not joining the class, so I'll explain it quickly again. You have your NRZ data, goes into the real-time latch, and that real-time latch is actually clock with a system that is now controlled by some kind of a reference clock, which is matched into a phase detector that is done by comparing the phase difference, okay, between what's driving and what's actually coming directly from the outside, putting it through a loop, digital loop filter, and into a phase selector interpolator that basically just controls which of the phases of the VCO is best aligned with the phase of the incoming data. And once that is locked, then you're free to pass it and start retiming the data as well. Some of these are just for reference. I don't think I'll actually ask for anything like that, but this is phase interpolator PI-based CDR, so similar idea. And the frequency synthesis can be a loop, can be a global PLL. So you have actually multiple PLLs. You got a frequency synthesis PLL, and you have a phase recovery loop. So if you're an experienced PLL, sometimes you will do dual PLL systems, triple D PLL systems. Very dangerous if you don't know what you're doing, but you can actually make so many things work clearly if you have that kind of skill. Okay, this one here is a little different. So this one actually is called a DLL, which is the next section is basically on PLLs and DLLs. So I don't want to spoil the party here, but what it is, the difference between a PLL, so you got the frequency synthesis PLL, and then you have a local DLL shown in green, and it's actually pretty accurate with the way that it's controlled. And you guys tell me the difference between a PLL and a DLL, or the most critical difference you see this. What's missing on that DLL? Look at this. No clock. Okay, so a DLL is a delay lock loop that it basically controls voltage to delay. But it needs an external output in the form of, so it doesn't need a clock, it's just effectively voltage to delay. They're both very important. We'll show you why as well, right? But what this does is that effectively has a frequency synthesis loop that controls a delay loop. And that delay loop is actually effectively the clock now for phase recovery.
So only a differential clock is distributed from the global PLL up on there, right? The delay lock loop locally generates the multiple clock phases for the interpolator. In this case, it's basically you're generating 8 phases. Okay? They're all at the same frequency. So that's a plus. And then the DL can be per channel or shared by a small number, and the same architecture can be used in the forward clock system as well. Now, okay, so DLLs can generate different phases very accurately, but what can a PLL do and a DLL can't? Because it doesn't have that oscillator. It's lacking a few things. So the DLL is great; it generates all the phases. So for phase generation, a DLL, wonderful. It generates all the phases you want, simple topology, but it also lacks one very important functionality that a PLL does.
PLL's case doesn't use reference clock for a line clock principle. I guess the PLL would, for example, we have like feedback loop.
No, but the DLL is driven by a PLL. Right? So it's all stable. The problem is the DLL only works at the fundamental frequency. But a PLL, not necessarily. I can divide by and I can get all multiples of it as well, right? So DLL only at fundamental frequency. So we'll do PLLs versus DLLs. We'll do that on the next lectures as well. Okay. Phase rotator. Okay. So phase rotator, phase interpolators. So these things can be very expensive, so we don't want to overuse it. So we have 360 degrees out of phase. We can break it down into quadrants, and actually we'll do a quadrant example in the assignment and one in the final. I'll show you how that can be done for the phase interpolator. Got some neat examples that we'll do in the next few weeks as well. So phase interpolators can be expensive because they actually end up producing phases that are not always used. If we could have a way to actually just block the phase using one oscillator, that would be great. But in this case, we're often generating 8, 16, 32 times the phase. That also generating power. That's a problem, right? So the phase rotator PLL places point interpolator in the PLL feedback and adjusts the VCO. Kind of has to find that. But the other 7 or 15 around it are actually not used. And now the frequency synthesis and phase recovery loops are actually coupled, right? So you have you got a frequency synthesis loop with a reference clock, and then you got a divided by 25, right? So look at that. That divided by 25 is actually compare, and then you actually have the PLL controlling the actual phases, and that goes into a MUX that actually interpolates all those values back for us. Okay, here's an example of a very simple interpolator. Okay, so what does the interpolator does? It interpolates between two values. So if you have A out and B out, and A out is a little bit down and B out is a little bit up, the actual time average output is actually a line. It does an averaging of it. So phase interpolator do digital to phase conversion. So you got two digital blocks, right? And they're off a little bit. And it basically changes the phase of that. Because look at this. If the phase is actually measured as a function of time, right? So you got a phase and you got time, but if the time is actually shifted, we in fact are actually doing phase control. Just by shifting the same signal in time, the actual measurement window that we have changes, we have to define a different phase. So phase interpolators do digital to phase conversion. Okay? And it produces an output clock that is a weighted sum of the two input clock phases. We got an input clock phase A out, input clock phase B out, and then it does a time interpolation of that. How do we do it? We actually do it, I don't know if I have a circuit here showing, but we do it with tell current summation, interpolation, or we can do it with voltage, right? And then effectively, we actually do an IQ sort of diagram here to actually define the different types of interpolation that you can have. And you can have different types of interpolation. You can have sinusoidal and you can have linear. In this case here, As you imagine, this is basically a linear, but I'll show you here what you could do. So here's a sinusoidal interpolation. That voltage, right? Basically, first voltage, second voltage, and the average voltage as well. So x in phase is a sine of omega t, and x out of phase or quadrature is a sine of omega t minus 90 degrees. So that in quadrature, right? X cubed on the top, x in phase on the bottom. And then the actual output here is effectively a sum of all of it, right? It's a sine of omega t minus omega. If you combine all these two together, basically now can extract the values of A1 and A2, and then that condition is basically A1 squared plus A2 squared is equal to 1, which is a sinusoidal identity. Okay. And then you basically can have also a linear one. So you can have a sinusoidal interpolation, which is this curve here, or you can have a linear interpolation. Sinusoidal is more natural, it's easier to envision. Linear isn't, but often linear is actually easier to implement. Sorry, the other way around. Linear is easier to envision. Sinusoidal works best, but it's actually very difficult to actually work a weighted function that actually has squares within the circuit. Because in the first part, it's very easy when you do tilt currents, right? You have a tilt current that is giving you the I, a tilt current is giving you the Q, and we can just do the sum. That's easier to see. But having a circuit internally that is going to actually approximate 1 squared plus 2 squared equal to 1, and actually generate that in an analog domain at high speeds would actually be very complicated. I think the last one here. So this one is so very difficult to generate circuit that implements sinusoidal weighting. So a linear weighting is much more preferred. And there you go. Here you have the output phase as a function of the phase code, right? And here's how we actually do it. So if you look at this, we now have weighted current sources connected to a load. And that's effectively how this phase interpolation is actually occurred. So we'll do an example of these sort of timing diagrams next week. And then we also do an example of the divided by clock as well. Okay. Assignment 3, so it should be ready by Monday. I'll have it ready online. And I also will provide you feedback on all the assignments up to now by Friday as well. That's my goal. Yes.
Go over question 9.
I don't have it here with me, but put it on the Discord, and actually I just want to make sure that everyone gets it. Okay, so just post it there. What is it? You have the same question as well, right? Okay. Don't send me private messages, because all I do is copy, back, and paste. Okay. Sure. Yeah, we'll go through that, and then and if you still have questions, just keep on adding it. Right? I haven't seen anything. Did you guys add it already? Because I didn't see it on Discord.
I've seen this as like the general assistance.
Okay. Yeah, there you go. So I even forgot. It's 9 and 10. The one about the some guy who's doing that one. Okay. Yeah. All right. Yeah, I wasn't sure if I wanted to throw that in. I'll give you some hints, but we'll work on that for sure. Okay.
Is there like an example of this really defined like in a textbook?
For 9 and 10?
Yeah, something similar to that.
Well, that's what I'll give you. I'll just paste it in there. Okay, sounds good. Anyway, that's good enough for today. We'll continue next week.